Awesome, yeah, no problem. So where were we? All right, so we're moving on to the chemistry of the hyporheic zone. So back a slide, really. Wait, why am I not going back a slide? Okay, I guess I can't go back a slide right now. Anyway, so moving on to the chemistry and the ecology of the hyporheic zone, because really all those structures, what they do is they just allow surface water and groundwater to mix, which then generates some really interesting products. So with these arrows, in the light blue, we have stream water coming in, and then the dark blue again is groundwater, with them mixing at the end of their points. Oh, that's weird. So with the stream water, what it really generally brings, say in a nice natural stream away from human civilization, in a simple geology, will mostly just be oxygen and organic carbon. And groundwater will bring stable temperature and electrolytes. So on the temperature side of things, what that means is groundwater is generally always the average of the region, of the average air temperature of the region you're in. And that's just due to the fact that it's getting a bunch of inputs. Groundwater generally in the ground for anywhere, well, weeks to centuries to millennia. So it's got a lot of time to mix and a lot of time to average out that temperature. And then electrolytes, in the same sense, groundwater is in the ground for a long time. So there's a lot of a chance to dissolve rocks. So it'll bring chemical species such as potassium, calcium, chlorine up with it, which is all stuff we need. The reason Gatorade is so popular, and things that other things need. So really, at this meeting point between the stream water and the groundwater, we actually end up having a really good area for, buttons aren't working, really happy microbes that will be happy to grow, consume the oxygen, use the carbon, and then also take advantage of the more stable temperature in the hyporheic zone. So it'll basically, any seasonality you'll have or any change in temperature in the seasons will be dulled in the hyporheic zone. So these microbes are less likely to freeze over, or not freeze, but become too cold, too hot. It's a nice stable place. You can kind of think about the primordial sludge that some people talk about with the genesis of life. It's almost a similar idea. It's a stable place for chemistry to take place. And at the same time, from the groundwater is the electrolytes will come through too and help these microbes out. And so the one thing I haven't brought in yet with this meeting of stream water and groundwater is actually the fact that it's in the subsurface versus being in a stream, which ends up being really important. So what being in the subsurface means relative to a stream is we get basically three factors that come into play. The water is moving slower through the subsurface. As the water moves around these microbes that are generally adhered to the different sediments, different specific grains of the subsurface, you get a really high surface area. And then also with this kind of combination of the slower movements, high surface area and the microbes, you end up getting some really important chemical gradients. So back at the slow movement, basically what that means is the microbes have way more time and easier time interacting with anything in the stream water they would like to eat, break down, just have, well, for lack of a better term, chemistry with. And that example kind of comes from, if you think about like if you're hungry and you say you want to have 3 apples to fill your stomach, right? You're gonna have a Major League Baseball pitcher, like this in the stream, it's basically like a Major League Baseball pitcher throwing the apples at you. Your chance of catching them and eating them is not the best. It'll happen eventually. But in the subsurface, it's much more like that pitcher lobbing them to you. Nice and slow, gives you a chance to kind of uptake them, process what's going on, and go through the processes you need to make that apple useful for yourself. The same thing's happening with the microbes, having more of a chance to interact with anything they need in the water or would want to break down. In the higher surface area, to use the same metaphor, is in this case, you have a pitcher pitching at you. He's already lobbing stuff at you. And all of a sudden your mitt is 5 times bigger. The chance of the apple hitting in the apple or the nutrient, the thing in the water that the microbes want, getting to where it needs to go is way higher, or at least on the large scale when it comes to microbial colonies or some such as that. And then what the chemical gradient is between this slower movement and higher surface area, the water will come in, the microbes will react with anything in the water generally, kind of, if you want to consider it, the first layer of microbes the water hits when coming from the stream, in the stream water case, the microbes will consume all of the oxygen and probably a good chunk of the carbon. Admittedly, I'm no chemist, so I don't know the exact detail on that. And then behind them will become water without oxygen and with a changed chemistry from their byproducts. And they'll hit another layer of microbes that will then do their own chemistry that's reliant on different chemicals other than oxygen, other than probably still use carbon, but other than oxygen and some of the other, and reliant on the byproducts of the first layer of microbes the water encounters. And this keeps cascading through until you get a very diverse, continuous gradient of chemistry that allows many things, many chemicals in the water, good and bad, to have a chance to react and change into a variety of different things. And so we actually kind of step back. Now that we have this combination of a very biologically and chemically active zone below the stream, we can start considering what happens when things that as humans, we don't consider good to be in water. So like in the stream water side of things, we can talk about fertilizer runoff, phosphorus and nitrogen contamination, or metals, say from acid mine drainage, like a really high iron concentration from draining from a mine where you get those bright orange streams you can see either like in Pennsylvania or in California, which when those go through the stream water, they'll eventually end up in the hyporheic zone. And then all the microbes, so phosphorus and nitrogen coupled with carbon is, sorry, some biologists will probably correct me, but it's the vast majority of our biomass and of all other life's biomass. And so these microbes just inhale it generally if they're happy and they're a good spot, which generally they're happier, air quotes, in the hyporheic zone. So they'll really take in that those phosphorus and nitrogen from the fertilizer, break it down, change it. Like phosphorus can change species to just different things with different solubility. So it may become a solid, precipitate out. And a good example with nitrogen is that if you think about stuff like ammonia and ammonium, that can actually be broken down just into nitrogen gas, which then will bubble out of the stream and can be completely removed from the system. And that contamination is completely gone. It's not stored, transformed into completely inert species. And with metals especially, is where actually the chemical gradients come into play, where the metals generally won't, the first layer of microbes, when the water is oxygenated, metals will generally be soluble. But then eventually, once you get past the first layer of microbes, consumes the oxygen, the chemistry changes, and the metals will generally gain an electron and go from, say, like, I think it's, let me lose an electron. Shoot, sorry, my chemistry is lacking right now. Anyway, they'll change species in the same thing. They will precipitate out and become a solid and become stored in the stream bed, thus more or less removing it from the equation downstream. Oh, well, that format didn't stay. So on the groundwater side of things, can be similar. Once again, we have metals. In this case, unlike iron, I mentioned acid mine drainage, a really notable one actually is arsenic that's naturally occurring in bedrock. And arsenic has got a crazy chemistry, which I do not care to go into right now. And just point being, it is the same thing as the iron I talked about. It will change its charge from like a +2 to a +3, and then precipitate out and may change and just be removed from our water source. And on the other side of things, we have chlorinated solvents, which are generally traditional industrial waste, such as like a really classic one, I think would be PCB, which is a really big issue in the 20th century. The microbes in the hyporheic zone, and it's been shown a lot that generally chlorinated solvents will attenuate or basically break down in the ground when they interact with microbes, especially in the presence of carbon, which is what's being brought in from the stream water. So those will generally get broken down into just other less damaging species. And the beauty, though, of the hyporheic zone is even with these contaminants coming in, admittedly, it's not a perfect system. It's a natural system. So it's not built for what we might consider, 100% efficiency or anything like that. But what it does carry with it is, a little too far, is the fact that when the stream water, groundwater meet, come back up in the stream, it's going to go back in the hyporheic zone at some point. The portion of water that returns to the stream is going to return to the hyporheic zone. So basically the stream water with the addition of groundwater gets cycled through the hyporheic zone over the whole entire stretch of the stream before it can reach a receptor that may be vulnerable to the contamination or the issues with the groundwater. So what this does is allows stream water, in this case, at the end of the day, surface water, to be a lot more resilient to inputs and to have its chemistry be a lot more, well, I already said resilient, I was looking for a different word. For its chemistry to having to take a lot more for the chemistry for it to change, which makes it a lot more predictable, a lot more manageable, and can preserve our surface water resources, especially in this changing world where things are changing and things are unpredictable. It's good to have these systems that will tone down the change from inputs. And what this ends up looking like is on the left here, we have a nice clear lake. Good buzzword is it's oligotrophic. Clear lake, not many nutrients, beautiful, good surface water. You could almost drink out of that lake maybe. There might be some pathogens in there. And on the right, we have a lake with an algal bloom, high nutrients. You don't want to drink out of that. There's a good chance you're going to get sick. If you have a watershed with streams that have a good, strong hyporheic zone, you will be pushing the lake that is collecting all the water from these streams more towards this clear water lake. It is admittedly only one part of the tool we need to manage these resources, but it is a strong tool we can use. It's a passive tool that if we treat the system right, it'll produce this and keep producing it. And so in that sense, going back to the title, it's like the liver. It'll take things out. It'll regulate the chemistry of the blood of our watersheds, the blood being water. And another good example I brought in, I mentioned earlier, is this is iron contamination from acid mine drainage. Same thing, you do not want to be drinking this. You're going to get sick. And the hyporheic zone, especially coupled maybe with some wetlands, which do some similar things, will help this iron precipitate out before it can reach our taps. And so all in all, the hyporheic zone is this really beautiful natural system that becomes a bioreactor that just leverages biology and chemistry in a natural setting to allow things to react, to change, and to regulate itself. So it's a really interesting area of study. I worked on it in grad school, and I still have a strong passion for it, and I hope to come back to it someday. I just wanted to say thank you all for listening, and I hope you have a better appreciation for the liver of the stream, and that it's something that is really interesting, really alive, really useful, and has been kind of, at least for me, under my nose my whole entire life. I didn't gain appreciation for it until about 2 years ago. So thank you for your time. Yeah. Mm-hmm. 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 All right, so yeah. So to repeat her question, she was asking how long it takes after like a hyporheic zone forms in a stream by the additions of rocks and logs, which we discussed earlier. How long does it take for the microbes to really dig in, build their colonies, their assemblages, and the timescale on that for it to become an active hyporheic zone? And my answer is sadly, I don't actually know. I assume it'd be pretty quick because we're talking about microbes, and assuming it's natural sediments being delivered, like it's not sterile sediments from like some construction site, but natural ones allowed from erosion and like hillside erosion, it'll probably be on the quicker side because the bacteria exist, I assume would exist in the soils already, and it's more just about them entering a new setting and letting different populations grow and other ones shrink that basically succeed. So it's probably a pretty quick process, but I can't give you a specific answer on that, I would say, but it's on definitely below a human scale, if that helps. It's not like we'd set up a hyporheic zone that our grandkids would get to enjoy the benefits. We can do this, and then maybe in a month to a year, we could probably have it down to being useful, I would say. Yeah, Michelle. Mm-hmm. Yep. So to repeat that question, Michelle asked if we can do projects to restore or remediate Hyporheic Zone, and that is a big yes, which I'm really excited about. That's currently happening right now. People are working on different structures, such as, well, I mean, I worked on log jams. People are just allowing more wooded areas around streams, allowing some more of those rocks in, because the goal in like the last 20th century with waterways was to make them clear and have them engineered to move water. And the Hyporheic Zone doesn't necessarily, the things it needs doesn't necessarily move water the most efficiently, because it'll have some storage, it'll have pools, it'll have breaks in the flow, so they won't be going as fast. But so we're moving away from that more simplistic ideology of we need water to move from point A to point B quicker, away from our cities, to move logs downstream, to this more nuanced natural approach of allowing the water to sit, to turn over a bit more. And we are definitely able to engineer that just by simply adding rocks, allowing more wooded areas, allowing a bit more erosion around the stream, adding in sediments to streams that might not have it otherwise. We can do that as well. Yeah, so there's a lot of opportunities around that for people to join in and work on and study. And you become an engineer, like an environmental engineer, and add that type of thing to the stream. Yeah. Mm-hmm. Yep. Mm-hmm. Mm-hmm. Yeah. Gotcha. So the question is, what happens when you have like a clay-based soil in your stream, or that's kind of creating the area that the Hyporheic Zone would flow through? And my answer with that is to kind of answer your last point. It is pretty impermeable. So you would have a Hyporheic Zone. It'd probably be diffusion dominated, where really things would diffuse into it more than like what I talked about, which is more the term advection, which is something you can kind of push through with a higher velocity, or higher velocity relative to diffusion. And that wouldn't make it, so it'd be functioning, but on a human scale, it might not be that functional just from the flow point of view, because the flow through would be so slow. Also, it takes diffusion for it to fuse back out into the stream. And if there's any actual advection, water movement that isn't randomized through that clay, it's going to be super slow and on probably a decadal scale, if you're lucky. So it wouldn't make the Hyporheic Zone super useful. But from the ion point of view, clay will have a lot of ions on its surface. It's super small, it's charged. Clay's got charged surfaces. So that actually could be good, because it could catch the electrolytes from the groundwater, or it could just already be storing those things for the microbes too, because they build their colonies on the grain surface itself. But so it could be good from kind of a supply side of things, if that makes sense. But then at the same time, the pores, so with clay being so fine and impermeable, as the microbes grow, they're going to clog it too. That's something you kind of got to balance, is microbial growth with what's called bioclogging. As it grows, it will restrict the ability of other things to move through the system. So they might bioclog it too. So it's kind of a possible vicious cycle, I would say. So clay wouldn't be super useful in general. You might want clay mixed in with different sediments to get different environments and effects. Because I stuck with a super simple system of just assuming like you have like a sand layer below the stream, or like a fractured bedrock that's oriented kind of with the stream. But I mean, in real life, as everyone knows, everything's complex. So you might have like clay lenses, you'll have old stream deposits, and all these things can work together to get this really diverse chemical gradient and environment that you need for the Hyporheic Zone. So some clay is good, but if it's just all clay, you're going to want to engineer it differently or change it if we have human objectives basically involved in the system. Yeah. That's a really good question. So where's my, actually they can just hear me anyway. The question was if we can have something that's too material that's below the stream that's too porous and permeable that will just end up losing a bunch of water to the stream, or not the stream, to the aquifer and the groundwater below it. And the short answer is yes, but oh, sorry. But so the kind of the good news with the hyporheic zone is you still, what will happen actually when you have a losing stream like that, it'll make the hyporheic zone flows a lot longer. So you will lose mass to the groundwater. So you won't get as much return to the stream, but it also can increase the retention times in the hyporheic zone, which can allow different types of chemistry to occur as well. So it's also kind of a bit of a trade-off as well. And on the flip side of that, if you have a lot of groundwater coming up under the stream, due to like say like it's in a really steep area, really saturated hills, valleys next to it, pushing water up, you actually end up restricting the size of the hyporheic zone. So you get more stuff going into the stream, but you have less retention, less of a surface area. So it's, as always, it's a trade-off. Not a problem.
I sent that last one to Vicky only.
All right, we will be moving to questions in Zoom if people are ready.
Is there a lot of stream, sorry, is there a lot of stream engineering going on?
So far as I know, there's a decent amount. I admittedly have just gotten out of academia, so I've gotten the impression from papers there's a lot of reviews going on, but so far as in the broader professional sense, I admit I don't have a great idea of the scope just yet. I think it's hopefully it's turning its turning point this decade where it's going to be happening more, but that's something I don't know off my cuff, sadly. Mm-hmm. Mm. Mm-hmm. Yeah. Yeah. So Laurie Meehan, my mother, is asking some of the ways you can kind of set up experiments with the hyporheic zone and begin to study it. And to answer that in the field setting, which is the not controlled setting, what you'll do generally and traditionally is you'll take a tracer, which can be salt, it can be a dye, it can be there's some really interesting ones that deal with like oxygen chemistry, I won't go into. But generally we'll stick with a salt tracer, which is what I worked on. It'll increase the conductivity of the stream just by dissolving in. And then we can put probes in the stream bed along it and begin to observe some of the retention in the stream. And if people can see, I would love to leverage this whiteboard to actually elucidate on that. Okay. Oh, good marker too. Okay. Time. And then conductivity. So we're looking at a time and conductivity graph here. So this will be a traditional tracer test. So what we'll do is we'll input the salt in the stream, jump right up, we'll be hitting the highest concentrations. And generally what we'll do is we'll kind of continuously give it input for a while to allow the salt to interact with flow paths that are below the stream in the hyporheic zone. Because if you just dump it in once, it won't actually interact with all the flow paths. So you just leave, so the conductivity will be up for a while as we're injecting. And then at this point right here, we'll stop injections with a tracer test and observe how the conductivity degrades through time. And that can give us an idea. So this, kind of like after that, we call that a tail. After we finish our injection, gives us an idea of how long things are retained in the hyporheic zone and kind of act as a proxy for the amount of stuff in the hyporheic zone and the amount of time it's in the hyporheic zone. So with just this kind of study, you have to do some other things and some numerical modeling, computer modeling to get an idea of how big the hyporheic zone is based off of parameters from your system. But this is a super traditional way to study this different type of flow in hydrology. If you want to get a little bit more into it in the field, also what I worked on, I used electroresistivity, which is a line of electrodes that you put cross-section perpendicular flow in the stream. and then we'd fire off and read voltages. So it's reading the same thing as like conductivity or resistivity, but there's a bit more of a spatial average, because this is when we're looking at stuff in the stream, it's only sensitive to things that return to the stream on the scale that we're looking at. So if we have like, if we inject in a stream and then we put a probe 50 meters down, we're going to only see things that have entered the subsurface and then have exited 50 meters downstream. But there's plenty of flow paths that will exit further downstream, so don't get the whole picture. And with electrical resistivity, what it'll do is it basically just takes an average of the whole entire geologic system below the stream. It's really hard to put a volume to it, but basically just imagine the whole stream. All sediment below it and stuff, to say up to like, I don't know, probably can get information from like 30 feet, give or take, but it becomes a little less useful after that. Depends what stream you're into. Anyway, and so with that, then you can also do some numerical modeling. Because you have the spatial average, you have more information, and then you can start actually figuring out the spatial distribution, or the area in space the Hyporheic Zone is in, due to increase in predicted increases in conductivity below the stream they've built from this electrode information. And so you actually use the same two methods, is what I did. These same two methods in the controlled setting is it's actually, I love it because it's a glorified sandbox. A thing called a flume, which is just this channel in a lab. You fill with water, or you fill with sediment, and you run water through it. And you can just control a lot more of what the attributes of the system are. And so I called it my beautiful glorified sandbox, and I loved it. And that's kind of some of the things that you can do to study it, and what I did as well. Oh, my bad. Oh, okay, cool. Gordon Gottschalk asked about animal communities that live in the zone. And so I focus mostly on the microbes in this talk, but he is right. It's, two of the big effects it has, with especially the stabilizing temperature in the zone, or the more stable temperature in the zone, is macroinvertebrates. So think about stuff like crawfish and different like bugs and critters will love to kind of burrow into it, and we'll find a home there too, and like a safety. It's like called a refugia, like a refuge for them to be safe. And I think they will usually feed in the biofilms too. Some of them do. So it kind of becomes part of the food chain with them. And then also with the type of water that can be upwelled and more stable, fish will spawn in areas where the Hyporheic Zone is returning water to the stream. And it's a super important part for fish spawning and for fish nests and eggs as well. So hopefully that answers your question, Gordon. And then I think you had another question too. Okay, cool. So then we have one more question here. So, okay, cool. So this is one of the courses I took to learn about it, and I talk more about my graduate work and experience. So far as courses, a lot of the stuff in my graduate work, I covered a lot of ground. And I think the most useful course for me was a course called Hydrogeochemical Processes, which attempted to couple together basically flow in the subsurface with geochemistry. Was the most useful one, I think, for me to tie all these ideas together. Otherwise, though, what I did in grad school was I took a lot of the broad strokes kind of ideas from classes. I took a surface hydrology class, basically a geostats class that taught me more coding in MATLAB, a subsurface transport class, but from a contamination, like a contaminant perspective. So I had all these things, really broad strokes taught, and then I ended up actually going to a lot of the literature to teach myself the exact kind of the nuances of the Hyporheic Zone. So for this, to learn about it, you really just need a good, solid, a decent grasp of physical movement, so it's called transport in hydrology, and then also an idea of just some of the chemistry as well. So just think geochemistry or hydrogeochem is a good one if you want to study it as a whole, but you can also just come from a transport perspective too, which is just the physical movement, or you can come just from the chemistry perspective if you want. But as currently we are in a phase, which I think maybe one of the professionals in the room can tell me this, we generally cycle through interdisciplinary studies every 20, 30 years, I think. And we're currently in a phase where a lot of the disciplines, or in that cycle, we're in the phase where the disciplines are really trying to cross over and communicate. So it's good to have all that under your belt currently. And with my graduate work, to kind of continue answering that question, specifically what I was studying using the methods I talked about was how multiple channels in a stream interact with log jams to produce the hyporheic zone. So like in that case, what we're looking at, people see me like over here. Yes, okay. So what I mean by multiple channels, so we got part of our stream boundaries here, and then just like an island in between with a stream flowing around it. So I was studying how that interacts with channel spanning log jams. Well, that's a terrible log jam. With a channel spanning log jams and how that changes the hyporheic zone, how it interacts with that. Because in this talk, I focused primarily on things that were like in line with the bed of the stream in kind of a cross section, but you can have effects more laterally as well, in more of a horizontal sense in the stream. So I was studying that, and hopefully I answered the question. But predominantly, I focused on the stuff in cross section because, as I kind of mentioned earlier, with one of the questions about groundwater coming into the stream, streams are an extension of the water table in the groundwater system. So along the edges here, you'll have a lot of groundwater discharging into the stream, which will restrict the hyporheic zone anywhere except for like right kind of like through its middle is where you'll find most of the action if you're in a kind of a normal groundwater system. And it can be different, there's a lot of different geologies and stuff, but so you can kind of do that. So like you can also look at like meanders and bends, they'll have effects on the hyporheic zone, you have water flowing through them. Multiple channels can do that. With multiple channels, you can get flow driven across the island. You can get more flow kind of along the edges here where like the island, where the break in the island occurs. And I just dropped my marker, hold on. Oh, I'm sorry, people on Zoom, that's really hard to see, isn't it? But anyway, yeah, so there's a lot you can do. So my graduate work was kind of more in the horizontal sense, if that makes sense. And then along with how it couples with different amounts of log jams, as well as a strong as an obstructing force to flow, which generally obstruction means hyporheic, if you want to have a takeaway from this talk. Any other questions?
All right, thank you all for coming, either personally or in person or on Zoom. Next week, we have Kathy Reese will be speaking. Kathy is a professional who works locally on rural community water systems, so that'll be very interesting as well. And that will also be in person and on Zoom, just like today's was. So let's all thank Sawyer again. And that's it. Thank you very much.